Hello students, in the previous lectures we have calculated the dot and cross product of first two vectors, then three vectors, then four vectors, and generalized it and then find the inverse of the vector. Now we will find the limit, continuity and differentiability of a vector point function. So for that let's compare the let's define and compare the vector point function and what is scalar vector point function, what is scalar point function. So let us define scalar quantities and vector quantities. You have read it in the plus one class that scalar quantities are those physical quantities which has got magnitude only, and vector quantities are those quantities which has got magnitude and direction too. Now let us define scalar. If it is a scalar quantity, let's define scalar point function. So scalar point function, function, whatever whichever functions we have studied in differential calculus in first year, we have studied their limit, we have studied their continuity, we have studied their differentiability, we have studied their integration, and we have drawn their graphs. So all those functions are we have studied in the first year differential calculus were scalar point function or scalar functions. We studied their domain, we studied their range, we studied their oneness, ontoness, and other things. Now we'll study the limit and continuity and differentiability of vector point functions here. So let us understand, let's compare them and let's set them. So now we know scalar point function. Uh, let this let these are two sets. DF is one set and RF is another set. Then a function f is defined to a rule which assures each value of x belongs to Rf, the unique value of y belongs to Rg. Therefore, and f is a rule, so we write it as y is equal to fx fx, and we have drawn the graphs as shown in this graph. X is from here, y is from here. So these are scale point functions. We found their limit at a point, and we have discussed their differentiability, we have discussed their continuity, and etc. Now, in a similar fashion, if we have two df and dr2 non-empty sets, and if this rule become a vector, this rule vector, and x is what is this x is a scalar point variable, scalar point function, scalar point variable. This. So for that, then this will become a scalar point function will become a, what will this become? This will become a vector point function. Vector point function. So let's get a vector point function. Let df be any subset of real numbers. Df is a subset of real numbers. Then a vector function f vector is defined to be a rule. This rule, as we studied in the scale point function, rule. Then vector is a rule which associates each scalar t belongs to df. Now in place of x we have each scalar t. X is also scalar. Now in this vector we have replaced x by t only, because yes, right? X in the differential calculus for scalar. Similarly, in the vector in this vector calculus, we have replaced x by t. Notation only this, but replace x by t, but t is also stable function as we mentioned. For just differentiation, now to df. Uh, A unique vector f vector t belongs to the codomain of df, then is called the vector point function of a scalar variable. So what is this ft? Uh, this rule is a vector. This rule is a vector. If you put a vector here, side vector here, this become Now this structure become a vector point function. Vector point function, right? Vector point function. Now, if the vector function R vector varies continuously with respect to variation of any scalar variable t. Now in the text we are writing t, and we have a direction of this rule. Then R vector is said to be a function of time and is written as R vector, written as R vector or R vector t function of time, or we let R vector is equal to f vector t, vector of t in this case. E.g., for example, the position vector R vector of a particle moving along a curved path is the vector function of time. Particle moves on a wall, particle moving on a wall, and particle or an insect moving on a wall. Wall is a two-dimensional geometry, or any insect um, mo- moving on the roof of the house, or just flying in the air. That the insect never move in a straight line, so that moves in a path. So the position vector of the point r, what is r? R is the position vector point with respect to the reference of axis. If it is in two dimension, so the whole two dimension. If it is in space, that is in the three dimension, three dimension. So this is what we have done about the vector point function. Means this is a suppose we are talking two dimension, particle move from A to B, and at any time t, particle at P. So P, this OP is the position vector of P. Position vector P, and because particle move from, this is a function of time. Particle is moving from A to B, a function of time. So we write the R vector position vector point P is equal to R vector is equal to F vector T. This is a vector point function. P is a P. Position vector P is the vector. This is vector point. So now we'll discuss the limit of vector point function. So the limit of a scalar point function we have studied in the differential calculus. Only the arrow will be put on the vector point function and vector function scalar function and their limit. Others domain and neighborhood, they all will remain the same. So let us define limit of a vector function. A vector function ft is said to tend to a limit L vector. F vector t is said to limit L vector as t approaches t naught. As t approaches t naught. T approaches t approaches t naught. T naught. That is, what is the meaning of this? This is limit t approaches t naught. F vector t is equal to L vector if for given epsilon greater than 0, however small, there exists a positive real number delta such that f vector t minus L vector modulus is less than epsilon for 0 is less than t minus t naught is less than delta. Delta is the definition of limit of vector function. So now let me compare what the difference between the limit of a scalar function and limit of a vector function. Limit of scalar function we have studied in the differential calculus in first year, and limit of vector function we are studying in the vector calculus. Now, if I compare both definitions, the both definitions are same. In the case of differential calculus, we have studied the magnitudes only, but in the case of the vector calculus, we are studying magnitude as well as the direction. Means only if we find the limit of vector function, means the if vector function converts to a vector only if t equals to t naught. So only arrow will be put on the in the definition of the scalar point function, you will get the definition of the vector limit of vector. Now algebra of limit of vector function. As we know that we can add and subtract vector functions, we can add subtract vector functions, vector function, vector point function, and we can multiply them. Multiplication will be of three types. Number one is we can find the dot product of two vectors, we can find the cross product of two vectors, and we can simply multiply a scalar function with the vector function. Simple multiplication. So we have, in the case of in the vector calculus, we have three types of multiplication. We can add, we can subtract, and so uh, we have three multiplications. So we can find their limits. Now we'll discuss how to find the limit of, if the limit of two functions are given, how we find the limit of their sum, how we find difference, how we find their product, dot product, limit of the dot product, limit of cross product, and limit of the if you multiply a scale product with a vector scale function with a vector. So for this, the limit of sum and difference and product of vector function are same as those of the scale point function studied in the differential calculus of BC. So we cannot divide a vector by another vector, so limit cannot be discussed for such cases. So we can't divide by division in the vector field is not possible. We can't divide by two vectors, so we can discuss the limit of their quotient. So let's discuss the technical. So limit t approaches to 0, t approaches to t naught, t approaches to t naught of f vector t plus minus g vector t is equal to limit t equals t naught of f vector t plus minus limit t equals t naught of g vector t. Second is limit t equals t naught of f vector t dot g vector t is equal to limit of limit t equals t naught of the cross product two vectors is equal to limit of their cross product limits. Limit of the limit t approaches to t naught, limit t approaches to t naught, t approaches to t naught of scale product of scale point function into vector function is equal to product of their simple product of this is simple product, this is simple product of the is to where f vector t and g vector t are vector functions of the scalar variable and phi is a scalar point function or scalar function of a scalar variable. Now fourth is if f vector is in component form, we are discussing it in the we have any sectors, any particle moving in the three-dimensional space, and each component is a function of time, function of the scale point function. Then the limit of that will be limit of this equal to L. L will also the three component. This means if limit x t approaches to t naught of f t approaches to L vector, then uh, first vector f1 vector limit t equals t naught of first vector will be L1, limit t equals t naught of f2 will be L2, limit t equals to limit t equals to t naught of f3 will be f3. Okay. So if that is if limit t equals t naught of f vector t is equal to L vector, when will this be true? If the first component will converge to the first component of the limiting vector, second over second, and third vector third. If first component converges to first component, second converges to second component, third component implies limit t equals to t naught as t equals to t naught implies limit t naught of f vector t equal to f. So now quantity of vector point function. Now let me compare with the quantity of a quantity of a scale quantity. Now again, there is no difference in the definition of the quantity of a scalar function and quantity of vector function. Only difference is that in place of in the case of the definition of scalar function, quantity of scalar function, we put the arrow over the functions only. Other or and the neighborhood will be the same. Not directly, but neighborhood will be the same. Limit was discussed in the limit was discussed in the deleted neighborhood. Limit was discussed in the deleted neighborhood point. Limit was discussed in the deleted neighborhood point. This is was in the deleted neighborhood point. Deleted neighborhood point. Deleted neighborhood point. Same as we discussed in the differential calculus. Limit of function differential calculus, and quantity also discussed in the not deleted but neighborhood of a point T naught, and we just put the vectors arrows on f-t and f-t. So this was fa, fx minus fa. Here is the ft vector t minus f vector t naught, which the t is equal to. So, and for all, this is equal to super. This is equal to, not just define it. A vector function ft is said to be continuous at t equal to t naught if for any given epsilon greater than 0, however small, there exists a positive real number delta such that f vector t minus f vector t naught modulus is a function for t minus t naught modulus is a function. If we discuss the quantity of a vector function in its domain, if the vector point function is continuous in whole of the domain, then that vector function is said to be continuous vector function. But if a vector function is continuous in whole of its domain, then that vector function is said to be continuous vector continuous vector. Altogether continuous vector function, if it is continuous. A vector function fx is continuous in continu vector is continu a vector point function is continuous if each of its component is continuous scalar function, continuous scalar point functions of a scalar variable. Scalar variable. Now, so we have defined the limit of a function. We have defined the quantity of a you have defined limit of a scale function. We defined the quantity of a scale function, and compared with the limiting quantity of a scale point function. And after comparison, we come to the conclusion that only average will be put on the scale point function in the equality of in the first equality. Other neighborhood and neighborhood will remain the